Well, I wanted to introduce Colin, but first, my name is Faraz Fadavi. I work in the Cloud and AI security team, building machine learning detections for our security products. I'm going to be introducing Colin O'Brien. Colin has been working in detection and response for his entire career. He started his career at Rapid7 and then moved to Dropbox, where Colin is currently working full-time on his project, Grapl, an open source detection and response platform.
Actually left Dropbox like 2 months ago.
Left Dropbox 2 months ago?
Yeah,
okay.
But very close.
Very close, still working on Grapl.
Yeah.
Let's everyone put our hands together for Colin.
Okay, thank you. I'm Colin O'Brien. I've been working in incident detection and response in some form or another for my entire career. I started off at Rapid7, and my first role there was actually on a data science team where we were trying to apply machine learning and sort of operationalize that as it applied to the logs that we were collecting for some of our products. Eventually, I started working more directly on the Insight IDR product, building detections for customers, building out scalable services, and new features. I decided that I wanted to get more hands-on experience in detection and response. And so I left Rapid7 and I started working for Dropbox, where for 2 years I was working directly on the detection and response team, engaging with our red team, having a lot of fun, and really just seeing what kind of problems that team was trying to solve day to day. These were a bunch of different types of roles, and they taught me a lot about how different groups are trying to solve a lot of the same problems. So today I want to talk about a project that I'm now working on full-time called Grapl. Grapl is an open source detection and response platform, and its really just main goal is to try to make data as easy to work with, as easy to manage, to query, to join as possible. And one of the ways that it does that is by leveraging the graph data structure. And so I want to talk about why I think that graphs are a really excellent abstraction and a really excellent fit for detection and response, and then prove that by showing you how Grapl is actually able to leverage them. I apologize in advance. I'm going to probably try to speak very quickly for some of these slides so I can get through everything. So I like to start off with a graph like this. This is a very sparse graph. There's not a lot of data. There's not a lot of labels in this. We can talk about nodes really only in terms of their coloring. But a graph like this can still express a lot of really interesting information. In particular, we can say things like the green node has a relationship with the blue node and the blue node with the purple node. We can say that the green node has no direct relationship with the purple node, but that there is a path between them. And the reason why we can say these interesting things is because graphs are really excellent at encoding relationship type information into their structure. This is one of the reasons why graphs are so powerful for things like data visualization, but it's a much more general purpose property of the data structure. Really, graphs are just excellent for any time you have data with lots of relationship information and you want to talk about those relationships. These relationship-heavy workflows are found across a number of industries. Google's search engine is powered by a graph. Facebook's public interface is graph-based. Graphs are powering machine learning libraries like TensorFlow. And they also tend to sort of emerge from systems. So the internet and BGP are sort of these emergent graphs. A little closer to home, we see graphs leveraged for financial fraud and abuse detection, answering questions like, is this user's identity stolen? Is this a shell company? Things like that. So of course, in the information security world, as this entire workshop is really a testament to, we're starting to see graphs gain a lot more traction. Years ago, John Lambert wrote this post, and in it he states, defenders think in lists, attackers think in graphs. As long as this is true, attackers win. And in the post, he gives a very concrete example of this list and graph-based thinking. He describes a situation where defenders are tasked with protecting a network. One of the first things that they're going to start to do is create lists of domain admins, lists of high-value assets, of risky users, of exposed services. They're going to prioritize the work that they do based on those lists. This is very different from how attackers go about doing their jobs. Attackers are opportunistically taking over whatever asset or user they can manage to. And they're going to leverage the capabilities they get from that to start moving across your network. This could range from taking over a compromised email account and using that to phish other members of that organization, or as Lambert talks about, dumping credentials from memory using a tool like Mimikatz and then logging into other assets. While the defenders are focused on these lists of isolated assets and users, the attackers are focused on the trust relationships between them and how they can abuse those to take over more of the network. According to Lambert, this mismatch in approach is so significant that defenders simply cannot win without a major shift in how they think. At the end of his post, he has a quote that I like. He says, "Manage from reality because that is the prepared defender's mindset." And so I think there's a more general statement being made here. It's not graphs are the best data structure. It's not lists are bad. It's that when you have data that matches a reality, the way that a graph maps so nicely to a network, or an attacker's traversal maps so nicely to a graph traversal, you lose something when you force that data into another data structure. And in this case, we're losing that ability to talk about trust relationships. One tool that very clearly demonstrates this shift in thinking is Bloodhound. It's gotten a couple of shout outs today for a reason. And that's because Bloodhound allows you to really shift the way you think about protecting your environment from asking questions like, who are my domain admins, to questions like, how do I start cutting off paths from an unprivileged user to a domain admin? And I think that that tool starts to reflect the reality of how attackers think about taking over these systems. So in detection and response, the sort of primitive unit of information that we leverage is the log, these representations of events across our networks. And we collect billions and billions of these logs every day, and we store them in what's called a SIM, an event management system. It's essentially a massive index, or in many ways a massive list of individual isolated logs. And we can take some of these logs down as we see here. We have a couple of logs next to each other, and we can see that they express properties about the events, right? A process execution will have things like the PID and parent PID, a timestamp, maybe a process name. What the logs are failing to express is that these are not isolated individual events occurring throughout the network, but in fact there are relationships between them. A PID in one log is shared as a parent PID in another log. We see IP addresses, domains, file names shared between them. And when we start to pull these relationships out, when we start to express our information as a graph, it starts to match the reality of the underlying information a lot more closely. We can reason about not just individual events and their properties, but how they connect together. And so Grapl really aims to take this graph-oriented approach, similar to what we've just seen on that last slide, and use that as its foundation. So what you would do is send raw logs up, currently supporting sysmon or just a generic format that you can target. It's going to turn those parsed logs into subgraph representations. So a process execution log would generate a subgraph with a parent process node, a child process node, and an edge between them. These subgraphs are going to go through some pre-processing and in particular something called identification. Essentially, we want to describe the actual identity behind these nodes rather than think about things in terms of PIDs or process names. In real time, as this data is being streamed up and processed, Grapl will merge these subgraphs into its master graph. So it's going to be this massive graph database describing all of the entities and behaviors across your environments. Again, in real time, Grapl will execute and orchestrate the execution of your attack signatures, or what it calls analyzers. And these are going to look for suspicious subgraph patterns in this master graph. And finally, as Grapl correlates those analyzers' output together, it's going to give you a tool for really drilling in and understanding the scope of what an attacker is doing in your environment, called an engagement. And so I'm going to talk about how these different components work. But as you can see, it's really very graph heavy. We use logs only as this sort of underlying, almost assembly language for building up these higher abstractions. When I talk about graphs in Grapl, I'm really talking about what you see here. These are representative schemas for what is currently supported in the master graph. We have nodes like processes, files, connection nodes, assets, and users. And we have properties on them that you would expect, things like a process having a name, a file having a path. There's also edges that are both explicit and implicit. A process has children, and as a corollary, it has a parent, which is the reverse of its children. Not shown here is the dynamic node that's used for plugins. An example of a plugin is I am building an AWS plugin. It takes guard duty logs, and it'll generate nodes like EC2 instance, IAM user nodes, guard duty alert nodes, and you can start querying those as well. I'm not going to go into the plugin system today, but keep that in mind. You can extend this very arbitrarily. I mentioned identity earlier. Identity is really important to Grapl, and I think important in general. Logs don't express identity very well. they tend to have things like PIDs or paths, which are really just pseudo-identifiers. They can be reused. A PID gets recycled once a process has terminated. And so if we have some logs that have the same PID, you might be tempted to believe that they're referring to the same entity, but that's not necessarily the case. Instrumentation tools like Sysmon will apply things like process GUIDs. Grapl is going to do the same exact thing, but it'll do it server side, and it's going to do it past that log parsing phase, which means it doesn't matter what the underlying log structure was. It can be from OS X, Linux, Windows, it doesn't matter. It's going to map these to canonical identities. This solves problems like PID collisions or being able to refer to a file that's been deleted and then recreated. But when we combine that identity concept with our graph, we get something really, really powerful. We can imagine a situation where we have this master graph on the right, and that's going to have a single node with a PID of 100. A process execution log comes in, and it's going to generate this identified subgraph that gets merged in. We can throw away that parent process ID. We've already stored it before. The type information doesn't have to be stored as a string. It's just going to be encoded directly into our master graph. We're starting to summarize our data and throw away redundancy. And this effect really starts to compound quickly. If that child process creates a file, we can throw away things like the process name and the PID that are involved. If it were then to subsequently read that file, we're throwing away almost everything in that log because it's just redundant information. This can lead to really significant, like orders of magnitude better data storage properties. And it goes to how Grapl is really intending to make the data as easy to use and to manage as possible. Next year, when you double your data ingestion volume, you're not going to have to like buy a new license or like go crazy over like hard drives and things like that. It should grow sublinearly with your logs. Great. So when it comes to detection, I think that logs and SIMs are what we've got right now, and we can do a lot with them. I think that SIMs tend to punish you for trying to join across logs. They make it slow. If you actually search Splunk's documentation for the subsearch or join commands, you'll find that they can time out and return incomplete results. So there's some problems with how we're optimizing those joins. I think this pushes us to create detections or attack signatures that are focused on one single log or a small, very small group of logs, and typically the properties expressed in those logs. The problem with this is it's brittle. We end up building signatures around things like hashes, IPs, and domains in the worst case, or in the best case, we try to create proxies through our properties for behaviors. Things like a process name with command line arguments means that it's probably this behavior. But again, the attacker controls all of that information. As an example, we can take these two process creation logs here. We have Word and PowerShell executing. There's no properties telling me that anything is wrong here. These are both Microsoft signed, digitally valid binaries, right? They are executing in the vast majority of environments. Again, you can try to parse out the command line arguments for PowerShell, but I think it's kind of brittle and a losing game. As we've seen before, the logs are actually hiding the information that we care about. When we bring this out as a graph, we can see that it's not anything to do with Word executing or PowerShell executing. It's the edge between them. It's that Word executed PowerShell. And more fundamental to this attacker behavior is that there's a parent-child process relationship that is unexpected. An attacker might go after Excel or Adobe Reader or something that they have an exploit for. They might not spawn PowerShell. It might be a command shell. They might bring their own binary. But what they almost certainly are going to do is start creating uncommon, atypical process relationships. What we want to start to do is represent attack behaviors more to the core of what attackers are actually doing, less constrained by properties. We can still build property-heavy subgraph descriptions, things like Word or Adobe Reader or Excel spawning a child process that is not on some whitelist, right? We can leverage properties as we would with a graph, but we can also build really strong, just purely structural signatures. I can ask what a dropper looks like. It's a process that talks to an external IP address, creates a file, and executes that file. We're starting to get to the heart of really true attacker behaviors that don't have to do with incidentals or artifacts of what they're doing. So at this point, what we want to do is take these subgraphs and assign a label to them, in this case, a risk score. This allows us to differentiate between something that's going to happen quite often, but is still fundamental to an attacker, like a parent-child relationship that's unique, and then something much more suspicious like Word with a non-whitelisted child process. Really what we're doing here is just building up a really clean, structured, labeled data set. We have this massive graph database that's now our labeled data set. And so the natural next step is to start thinking about a model that we can feed this into. And it doesn't have to be anything like a machine learning model. It can be something very simple. In this case, what we're going to do is use something called a lens. Here we have an asset lens. And what that's really saying is show me all of the risky subgraphs within the scope of this asset, so like a user's laptop. Lenses could also be things like usernames or really any correlation point. Now we can look at otherwise isolated risks like the browser executing a file, which is like really an attack signature, but also something that's going to happen all the time, and see that it overlaps with a file being unpacked and executed, or suspicious network traffic, or dropper signature, that sort of thing. This is going to build up a composite risk score attached to that lens. We can not only look at all of the risks as they are isolated within this lens, but we can also see how they overlap. And because it's a graph, they overlap by default. If they're connected, we can see that. There's no extra operations to do correlation. We just get that sort of thing for free. The way that these attack signatures are actually written and expressed in Grapl is through the Python programming language. I don't want to get into like a holy war between DSLs and programming languages, but my short feeling here is that in 10 years, when attacker techniques have changed, and when we have to start scaling in expressivity to really encompass those attacks, I worry that a DSL created today is not going to do it, but a language like Python that's so general purpose might. To actually deploy and create one of these real-time analyzers in Grapl, you just have to implement this base class. It's really very simple. You inherit from the analyzer base class. And you implement two methods. There's get queries and onResponse, and they do pretty much what you would expect. Get queries in this case is returning a query for a process that is constrained by one of 3 process names, and that process must have spawned any kind of child process, and we're not constraining that child process. Grapl is going to take that query. It's going to optimize it. In many cases, it'll determine that this query doesn't need to run against the latest master graph updates. It'll ensure that it's a constant time query. So that means that next year, again, when your data size doubles, the query will run in the same amount of time. And then when you get a response, it'll call the onResponse method. We can perform subsequent analysis, which I'll show in a moment, or we can just assign a risk score and move on. Because this is Python, we can build really powerful interfaces and build much more powerful types of analyzers. Here you can see that I'm leveraging this parent-child counter. This is a specialized class in Python, and it's going to hide and encapsulate all of these implementation details. And from the caller's perspective, there's really not much complexity. We're saying count all of the times this parent process and child process go together. In reality, under the hood, that's going to hit a Redis cache that's going to do all of these optimizations so that in the vast majority of cases, it doesn't even hit the graph database, keeping this very efficient, essentially for free. Probably the single best part about leveraging a language like Python as opposed to a DSL or query language is how standard it is. If you were to Google search Splunk unit test, you would find that it is simply not supported. There are some hacks around that, but nothing's really going to come close to just going to Python's standard library and importing unit test. Python gives you things like static analyzers, linters. You can put your code in a GitHub repo and enforce a code review before pushing it out to your deployment. And actually, Grapl has a plugin to do exactly that. This really goes towards alert management, which I think is a very overlooked issue. It's not uncommon for a team to have over 100 different attack signatures easily, and that could amount to thousands of lines of either your query language or Python. But SIMs and vendors don't really make it very easy to test those out and ensure that your attack signatures today are going to work in 6 months after everyone's been tweaking them in little ways. When it comes to investigations, I think that the log-based workflow can suffer in a couple of ways. And I want to try to demonstrate that by doing sort of an example of a log-based investigation. So a log-based investigation will probably get kicked off with something like an alert saying, this log contains bad information. And in this case, we'll assume it's like some threat intelligence feed telling me the hash for this process is evil for whatever reason. What I'll do is go to my SIM. I'll open a search window. And I'll start saying things like, I'm going to search for this information over the last couple of hours, right? I'll say 2 hours, keep the search window small so I can iterate very quickly on my queries. In a situation like this, what I generally want to do is try to quickly see what the suspect process has done. I'm not going to try to fully scope the attack behavior, but just get a glimpse. And then I want to trace it backwards and find where it came from. So let's see what the process has done. The only way I can really do that easily is just search for all of the logs with this PID. And I get a whole bunch of logs back. And I can see that it's doing some suspicious things, right? So time to trace it backwards. I'll search for the parent PID. What I get back is hundreds or thousands of logs. And it turns out that the parent is some legitimate process, like a scheduler, something like LaunchD or cron. What this is telling me is that the attacker has likely been on this asset for quite a while. And they staged this to execute weeks or months in the future, really just to mess with me. And you'll see how effective they are at that. So I can't pivot off of processes anymore to go backwards. We've hit this stopping point because it's legitimate. Let's try to pivot off of the file. I'll search for the hash, and I don't get any new logs. I'll search for the file name, and again, I don't get any new logs. And this is because the attacker is aware of the fact that I have a very limited scope of logs. I have to fight things like search query time. I have to fight things like log storage. At this point, I only have one choice. I'm going to have to expand my search window. I'll start to see new logs come in. Maybe these are things that I actually care about, like what created this file. But I'm paying a very significant cost. If the attacker created this scheduled task a month ago, and I just went from a 2-hour search window to a month-long search window, every subsequent query from here on out is hundreds of times slower. What's even worse than this is that I am basically guaranteed to start running into a lot of process ID collisions. You might have something like sysmon if you're a Windows shop, but in my experience with an actual attack or red team, you're much more likely to have to jump out of sysmon at some point and start using PIDs. And really, even after just an 8-hour search window, you're just about guaranteed to start hitting PID recycling. The other problem might be a little harder to see. Essentially, I want to ask simple questions like, what process created this process? The only thing I can do is pivot off of that parent process ID and get all of the information back, whether it's relevant or not. A simple process name would have been fine, but instead we have to search over hundreds of logs. Same thing with the process or the file creation. I'm trying to pivot to find what created the file. Instead, I'm getting everything related to that file, and I'm bounded to that search window. So Grapl takes a very different approach to this investigation process. And it's inspired by what I see data scientists doing already. Data scientists have been doing this job for years, and it's just what they are experts at, among other things. One of the tools that they leverage for this is the Jupyter Notebook. It's sort of like a super-powered interactive Python environment. It lets you execute Python code in little snippets. You can go back and edit it, inline markdown, inline images, really do all these crazy things. And it's the tool of the trade for data scientists who are building out models, who are cutting into huge amounts of data and trying to figure out what is going on. So as an analyst, what you'll do is you'll go to work, and you'll sit down, and you'll ask Grapl, what are the lenses and what are their risk scores for my environment, right? Those lenses are going to be the correlation points that join all of our risks together into something a little higher level. And I can see a bunch of assets here, and they have disparate risk scores. So most days, I would just start from the top. In this case, for the demo, I'm going to just take a look at this third asset lens, the desktop. I click on the lens, and what I get is a very compact graph representation. We're not talking about a graph with hundreds or thousands or millions of nodes. There's just 3 nodes because this is already a filtered, summarized data source, right? This might have taken tens or hundreds of logs to represent, but all of that data would be thrown away if it was redundant. I can click on these different nodes. I can see that there's risks attached to them, different properties for them, whatever's been collected. And if I click on this command.exe, what I can see is that it's actually involved in 2 different analyzer outputs. One is this sort of structural search, which is any unique parent of a command host. In this case, the binary called dropper.exe. We've never seen that execute command before. And the other is a much more property-heavy analyzer, which is going to say SVC host executing with any parent process that isn't on a very strict whitelist. These form together through this lens to build this composite risk score. At this point, what I want to do is open 2 browser windows sort of side by side. One of those browser windows will have a Jupyter notebook. And you can see at the bottom one of those cells from the notebook. I'm going to create an engagement with a name, and I'm going to use that process ID, or well, the one for the SVC host, that node key for it. I'm going to pull that into the engagement. That's the starting point that I want to begin pivoting off of. On the other screen, I'm going to open up the lens for that new engagement. And this is going to be a live updating graph visualization of the full scope of this attack. And because this is a graph, we can pivot extremely easily and extremely efficiently. I don't have to guess through something like a PID or a process name. I can say things like svchost.getParent. This is a constant time operation. Again, there's no search windows. It doesn't matter if command.exe launched a year ago. It's the same query no matter what. I'm not constraining it with timestamps or anything. And so what we want to do is what I said before. We want to take a look at this process, and then we want to start tracing it backwards. So in our Jupyter notebook, we'll do things like say, once we've got that reference to the process, in this case I'm calling it root, but you can think of it as that SVC host, we'll get its children processes. Again, these are all constant time operations that you see everywhere here, so it's very, very fast. This root process, this SVC host, has shelled out 3 different times. I'm not going to dig into that right now. We can just start tracing that lineage back up. We'll just keep getting the parent process. We'll say get parent, right? We'll get the parent again, the great-grandparent, until we get back to Chrome. And keep in mind that as I'm calling these get methods, this visualization is live updating, adding these new nodes into it. So keep in mind that this graph representation likely took over 100 different logs. In your sim, it probably wouldn't have fit on a single page, and certainly not in a single browser window. Instead, we have a really compact, information-dense graph, and it's not taking up a lot of room. It's not super interconnected or noisy. It's just showing us what we want to see. It's showing us what the attacker has done. And so at the end of your investigation process, you're going to be left with these 2 things. You're going to be left with a visualization, which is very compact, which you can show to other team members, show to executives or managers, rather than dumping thousands of logs on them, or even show to other security teams. I've had to go to a different security team before and say, here's my timeline, and here are the references into this like massive log search with thousands of logs in it. Like, I can sit down with you and we can go through it. Or I could just give them a graph with maybe like 24 nodes tops, which will represent a good amount of any attacker's scope. The other thing that we have is our Jupyter notebook. This is a codified representation of our investigation. The fact that it's in code leads to a lot of potential, a lot of opportunities. For one thing, I don't have to do the same work next time. I can start building out my own custom abstractions. I find myself doing this get lineage, or rather get parent over and over again process, right? But I could implement a get lineage method on the process query or a helper function, which can intelligently traverse that process tree backwards. And now next time when I want to do that, it's fast, it's available, and I can just keep it in my Jupyter notebook. This can also act as training materials. You have a new employee come in. You can clear out the visualization. You can say, here was an interesting engagement that we had. Just play through it, pivot off of the data, see what you can find. So a lot of this is really about trying to express the reality of the data, right? Getting back to what Lambert said about expressing what attackers are doing. Attackers are spawning processes. They're interacting with the network. They're interacting with files. It's extremely relationship-heavy workflows from the attacker perspective. And so when we start working with a data structure like a graph that can express them more concisely, I think it makes it a lot easier to work with that data and see what's really happening. I'm just going to talk briefly about setting Grapl up. It's extremely simple. Before I get into that, though, I do want to say Grapl is open source, and it runs on AWS. So really the goal here is to keep operational complexity as low as possible. The code is there. You can inspect it. You can see it. If there's a bug, if there's a performance regression, you can just go in there and find it. On top of that, it's going to run on serverless infrastructure almost exclusively. And that means that you don't have to worry about patching these systems. You don't have to worry about scaling. It will auto-scale. It'll do a lot of this work for you. So to set it up, you can clone the repository, go to the CDK folder, install some dependencies. You will have to fill out a .env file with a single parameter. There's some other optional ones as well around scaling. But it's just a bucket prefix, so an org name or something unique is fine. At this point, you run the deploy all script. This is a non-interactive script. You can go browse the internet or grab a coffee. It's about 10 minutes. And once it's done, all of your infrastructure for Grapl is up and running. It's extremely easy to get up and started with. There's only one more thing to do at this point. We have to provision those schemas in our graph database, which eventually I'll automate as well. But for now, you can go to the AWS console, go to SageMaker. Grapl has created this engagement notebook for you already. You can clone the repository into that notebook or copy and paste this graph provision notebook into it and just hit the play button. And at this point, it is 100% set up. It's ready for you to send data to it. Grapl's repo comes with test data. You can see that command.exe, that dropper.exe in the data already through some sysmon logs. You can run this script. It'll send it up to your instance. So hopefully I've been able to impress upon you why I think that graphs are such a strong fit for this sort of work. Relationships are just intrinsic both to how we work with our logs and how attackers are leveraging their capabilities against these systems. When we can leverage a data structure like a graph to expose that, we can work more efficiently. So with that, I'm not sure if I have time for questions. I tried to go as quickly as possible.
Unfortunately, no time for questions.
That's cool.
OK, thank you so much.
Great, so find me around.